2, 1, you are live.
Okay, welcome back, everybody. There were a couple things that I realized I wanted to talk about, but failed to during the last class when it comes to the paralleling of transformers with different phasing, specifically as it relates to this example. One thing that I wanted to point out is that in this case, the phasing was not an issue between T1 and T2. The issue with the phasing was between T1 and another parallel transformer that wasn't at the station. It didn't even belong to the same owner, right? It was a transformer. This transformer is owned by the local municipality. The transformer that it didn't phase with was owned by the local utility. So you got to be aware of that. It's not necessarily just the phasing at your local station that you need to worry about, the phase shift of the transformer at your local station that you need to worry about. It's anything that could be in parallel with the transformer, even if it's remote. So that's something to keep in mind. The other thing I wanted to point out is the phase shift of the transformer is, as we've talked about several times, but I don't know if I've ever actually, I know I've put it in the slides, like the transformer's phase shift depends on the primary electrical phasing. And then it's a matter of the rotation. Like I had said, if it's an A to H1, B to H2, and C to H3 connection for a positive sequence, then your phasing for the transformer, the phase shift for the transformer is going to match the vector diagram. And then if you swap any two, it's going to change that phase shift from positive to negative. And I explained that, but I never said that it, like, if it's A, B, C and you do any other phasing, it doesn't match, right? It's that sequence that matters. So it can be 1, 2, 3, or it can be 2, 3, 1. And that's still the same sequence, H1 to H3, or it could be 3, 1, 2. So there are basically 3 phased bushing connections that you can use to get a phase shift that matches the vector diagram of the transformer. And there are 3 that will be the opposite. So it's not, it doesn't necessarily have to be just A, B, C to H1, H2, H3. It can be any of those 3 sequences. So I thought that was worth pointing out. So I apologize for not doing that explicitly before. It's probably just something that, like, you know, in my mind, it makes sense, but I didn't say it. So I wanted to say that. And then the other thing I wanted to point out about this is I had said that we had changed the phasing on both the high side and the low side to change the phase shift. But as we just talked about, to change the phase shift, all you have to do is change the connections on the H1, H2, and H3 bushings. Does anyone want to guess as to why we changed the phasing on both the high side and the low side? Okay, guess not. So the reason
I don't even know the answer to that question. That's a tough one.
You don't? Oh, okay. All right.
You do it on both sides? I've never seen it on both sides.
Yeah.
So I've only ever seen it on one. So that's a tough one.
Okay. So we had to change it on both sides because the municipality had 3-phase loads. So we changed it on the high side to change the phase shift. But if we just change 2 phases on the high side and you swap the phases as it leaves the station and goes to the distribution customers, you've now changed the phasing at all of the 3-phase loads out on the 34 kV system, which means if they have motors or something, they're now going to spin backwards. And that was why we changed the phasing on both the high side and the low side before it left the station, so that it didn't impact the 3-phase customers out on the distribution circuit. So we changed this side to change the phase shift so that it paralleled with CMP's system. And then we changed the phasing back on the low side to keep the rotation at the customer the same.
That's pretty unusual though, because normally if you look at the phasing diagrams for your utility customer, don't they have A, B, C, or 1, 2, 3, like left to right over a pole? I mean, don't they have the actual physical phasing diagrams showing that? Or I thought I remember seeing some of those diagrams, and I understand about the rotation, but I figured there'd be just 1 or 2 cases where they would do that. But I'm going to defer to you, right?
Yeah, this isn't a utility either. This was a municipality, and like I said, they didn't even have the phases marked. They had no idea which phase was which. So they just hooked it up and said, yeah, that ought to work, which it obviously will, you know. And as long as the 3-phase loads, this station was built in probably 2010, maybe somewhere in that time frame. So when they built it, and then they hooked up their 34 kV customers, you do a rotation check at the customer and everything's fine and you're good to go, and you can put the station in service. But they didn't do a phase check between their 34 kV system and the local utility that they had the tie switch with. So we wanted to make the tie switch usable, so we had to change the phase shift, but then we didn't want to change the rotation at the customers, so we shifted it back. So that's kind of a nuance that I think is a good thing to note. And I meant to bring that up and I had forgotten. So I wanted to point that out. Does that make sense? Anybody? Do you have questions on that? That it changed, this changes the phase shift, but if you don't change the low side, it also changes the rotation. So we had to change it back on the low side to keep the same rotation and only change the shift. Okay. We left off discussing the drawbacks to YY transformers. I think I had gone through both of these, but I guess just as a recap, it was right at the end of the lecture. The YY transformers have a couple drawbacks. You get third harmonics, which are not good. Obviously, the voltage increase. The third harmonic voltages can actually be greater than the fundamental frequency. And you can also, if you have an unbalanced load, there's no path for the neutral current to flow if you don't ground the Y winding neutral. So there are two, I think this is where we left off, basically. There are two techniques that you can use with a YY transformer to avoid those problems. One is to ground the neutrals of the YY transformer, which now makes it a zero sequence source through the YY transformer, which is often undesirable. You want to have those isolated neutrals. It makes your coordination easier. Often, the utilities are really strong zero sequence source typically, and your industrial customers that might have a YY transformer don't necessarily want to see all of the ground fault current that's available to the utility on their system, because then they have to have bigger breakers or what have you. So they generally don't want to have the both of the neutrals grounded, so they don't like that. And then the other option is to add a tertiary winding, and we talked about that, how CMP specifically, when they do 115 to 12 transformers, they don't ground the 115 kV side. That gives them the isolated neutrals between 115 and the distribution, so that they don't have issues with exceedingly high ground fault currents on the distribution side, and it doesn't impact their ground protection on the 115 kV transmission line. And the delta tertiary resolves the problem with the third harmonics and also provides a ground source for the low side of the transformer, which is grounded. And now you can handle those imbalanced currents because you have imbalanced loads, and also provides a path for zero sequence fault current to flow so that you can detect ground faults. So if you're going to use a YY transformer, you must do one or the other. You must have a delta tertiary, or you must ground the neutrals of the transformer in order to avoid those problems. The second type, again, we're going over these four types: YY, Y delta, delta Y, and delta delta. The second type would be a Y delta, so Y on the high voltage connected winding, the high voltage winding, or a delta and a delta on the low voltage winding. Again, I've given the relationships here between the line voltages and the winding voltages. Same thing with the currents, and also the relationship to each other. This is, again, just more for your reference than anything else. As Paul pointed out, you guys have all seen this before, but I wanted to be thorough and make sure that the slides had all the information that you'd need. If the neutral of the Y winding is grounded, then this transformer acts as a source of ground fault current. I'm trying to be careful with my wording here. A YY transformer with grounded neutrals on both sides is a path for ground fault current to flow through the transformer, but it is not a source of ground fault current. Only the delta Y is a source, and that's really important. A lot of people don't recognize that, don't understand it, or don't remember it, but it's really important and worth noting. So delta Y, the Y side, is now a source for ground fault current. The transformer itself is a source of ground fault current. So if you have a ground fault on one of the high voltage bushings or phases here, the zero sequence fault current will circulate in the delta and be supplied to that ground fault. Whereas if this, again, if we go back to the Y and you have a ground fault on that same terminal, the zero sequence current is just the transformer just acts as a zero sequence path for that fault current to flow. It will flow through this neutral into ground, out of the ground, and into this neutral. So it'll only be a path, but not a source. So I want to make sure that's clear. Are there any questions on that? What the difference between a path and a source is? Is that understood? We'll get into the sequence diagrams and we'll talk about it a bit more, but I just want to make sure that that's clear what the difference is.
You may want to emphasize that again, because it's a subtle difference, but it's really a very huge difference in terms of that. And it makes sense to me, but yeah, I don't know if the students will really understand that the ground fault current can't go back in a YY or in a Y delta. It can head back to the fault. So that's why.
Well, that's true too. Yeah, right. So what I'm referring to is the zero sequence network, which we're skipping ahead a few slides. Can you guys hear the road noise? Should I close that window?
I can't hear anything.
Okay, there was a motorcycle that just went by. I just want to make sure that it wasn't bothering you guys. So a YY transformer that's grounded on both sides, the zero sequence network just has the zero sequence impedance of the transformer between the bushings of the transformer. So if you had a fault over here, you can, the zero sequence current can flow through the transformer. But if you have a delta Y or Y delta, the ground fault current from the X bushing side cannot flow through the transformer. That's an open circuit, but it does provide a ground reference. Okay, so it's a source of zero sequence current. So the ground fault current on one side or the other is isolated. The systems are isolated, but the transformer acts as a source. Okay, kind of. Maybe we can play around with this, right? I don't know if we have a good delta Y example. Here's one. All right. So if we put a single line to ground fault on this bus, let's take out all the other lines, make this really simple. and we put a single line of ground fault on this bus, right? You can see that there's actually no zero sequence current going into the delta side of the transformer, right? But there is ground fault current coming out of the transformer. Where does that ground fault current come from? The transformer itself. The transformer is a source of zero sequence current. Okay, if we put a ground fault on the low side, you may get some from the generator, but yeah, so it's all coming from the generator. None of this is coming from the transformer because zero sequence current, ground current cannot flow out of that delta winding. So it's not a source on the delta side. It is a source on the Y side. This is different than a YY transformer. Like this one, I think this is grounded on both ends. Yes, it is. Okay, perfect example. So if we take out all the other lines to keep it simple, right? We put a single line of ground fault over here. Okay, this has ground fault current in. It goes through the neutral and it just travels through the transformer and comes out and goes to the fault, so that you're not isolated for ground faults anymore like we were for the delta Y transformer. We had a ground fault over here. There was no ground fault current supplied through this winding. It just came out of the transformer. Okay, whereas here it's flowing through the transformer, and that's the only source. If you took this divided by that, you'd get the turns ratio of the transformer. So it's just flowing through, and it's flowing through the impedance, the zero sequence impedance of this transformer. It's not a source itself, it's just a path. Does that make sense? Am I demonstrating that okay? It's an important concept. So ask questions, if that's not clear.
So one of the things I could add, Andrew, too, is I always tell folks that what flows through the primary must flow through the secondary. So sometimes that helps to see how in the Y, you can see why it goes to the neutral, and it has to go through the other side of the neutral, because if it flows in the primary, it better flow effectively to the secondary. Where the delta, it can circulate in there, and then the Y, it can head back because you have that path. But in the YY, it's got to go up through the neutral and back. So that's why it can't head back to the source. It has to continue on. So I don't know if that's a helpful one, but that's always helped me understand, how the current flow is available or not, because it's kind of a nebulous concept. Even with showing this is useful, but it sometimes doesn't always explain why that occurs. So yeah,
that's a good way to put it.
Andrew, for clarity, where we did the delta Y example, if you let's say you had no generation, but you had it. I think, and I wasn't sure if I think you had everything open but the generator. But if you had the generator off and then you showed a fault over there, I think that might highlight that that better. If it's being fed, I guess, from a different circuit. So if you close a different circuit, feeding that bus.
Right, now you'll see it. Yeah. Right. That's a good point. Yeah. So even though there's no source on the low side of the transformer, great point, Blaine. Thank you.
Yeah, no problem.
Even though there's no source here, it's still supplying ground fault current. And this is how you'll hear people say a grounding transformer. That's essentially what it is. It's delta Y transformer with the Y winding neutral connected to ground, and the phase connections connected to the phases of the distribution circuit or transmission line or whatever. And now you've got a ground source on the circuit. So that's a grounding transformer. That's we talked a little bit about zigzag transformers. That's another way to do it, but usually it's a delta Y connected transformer. Great point. Thank you, Blaine. So for delta Y transformers, you no longer have to worry about your third harmonic issues. For the same reason, you could add a delta tertiary to a YY transformer and eliminate those as an issue. And now you have your ground source, your grounds isolated on either side of the transformer, which is great. And it also acts as a source of ground fault current. So this has got a lot of things going for it. The drawback is your 30-degree phase shift. So which isn't a problem as long as you understand that it exists and how to install the transformer in your system and how to set your relays when you have a delta Y transformer. And this is why, you know, in practice, 90% of the transformers you're going to see are delta Y grounded transformers. Yeah, and I think this kind of goes through that. No problem with third harmonics. Yeah, 30-degree phase shift is the problem, and that can cause problems when you're paralleling multiple banks together. It's customary to make the secondary voltage lag by 30 degrees. Although this is standard, it has not always been observed, and older installations must be checked very carefully before a new transformer is paralleled with them to make sure their phase angles match. So, yeah. And as I previously mentioned, it's not necessarily just at that station either. You know, if you're putting in a transformer at a station that doesn't have a transformer, you want to look at what the high and low side tie to. And if you're in parallel with another transformer at another station, you need to match that if they're going to tie. Okay. Delta Y transformers, same thing. Very similar to Y delta, it's just the ground source is on the other side. So usually you'll see like synchronous generators, they'll be connected to a delta Y transformer with the delta, well, kind of like this. They'll be connected in this configuration. And that's usually because the utility wants the ground connection. They like those. They help with their ground over current protection. Ground distance protection. They like the ground source. Also, a lot of times generating facilities or industrial customers, they kind of like the delta, because now if you have a ground fault, there's actually no ground fault current. So a lot of times they can keep operating during a ground fault. So I'll have some sort of detector that detects that you've got a phase that's grounded, but they can keep running, and they like that. So they can at their leisure go and figure out what the problem is and fix it without shutting down. So they like that delta connection oftentimes. The problem is if you have another ground fault on one of the other phases, and now you've got a phase-to-phase fault, and that's something you need to deal with immediately. But in the meantime, if they've just got one ground fault, they can go and try and figure out what the problem is, but without shutting down. Then for distribution customers, it'll be delta Y the other way. And that's like we talked about, this is because you want to have that ground reference for your distribution customers for detecting ground faults on the distribution circuit, and to allow load imbalance to have ground current coming from the transformer. And then the delta on this side, that's what makes it a source, and the source of ground fault current on the low side. And it also isolates the ground faults on the low side from impacting your higher voltage system. So delta Y transformers used all the time, 30-degree phase shift, pay attention. That's the summary. Delta delta transformers, again, just providing this as reference. You guys have been through this. And then delta delta transformers are not a source of ground fault current on either side, because ground current can't escape the delta, zero sequence current can't escape the delta. And they don't have the problems with third harmonics that YY transformers do. I don't think I've ever set protection for a delta delta transformer. So I think a lot of the distributed generation now has delta delta transformers. I don't know, Paul, maybe you know better. I haven't dealt with a lot of the DG
delta
stuff.
Y.
Delta Y, delta
They're
on
delta
the
Y for the
DG
ground
side.
source,
Okay,
because the utility still wants the ground source,
right.
because they've got to make sure that it's effectively grounded. So they want the Y, and then it's up to the end client if they want their AC system grounded or not.
Yeah. my understanding, again, I'm not an expert on distributed generation, but my understanding is a lot of the inverters require the that bus that goes to the generator step up transformer to be ungrounded. So they like that delta. But that's just hearsay, I guess. I don't know that for a fact.
I don't know about that, but you still have to do the effective grounding when you tie these plants down.
Right.
So you always will have an impedance, and it's either going to be delta Y. I think I have seen a YY when somebody did a zigzag and it didn't work, but most of them are delta Y. And if they do need a ground, they'll put a zigzag on the AC system for that high impedance ground.
Is it YY grounded on both sides or just on?
No, that was somebody who didn't understand exactly what you said about the difference between a source and a path. They didn't understand. They just assumed, oh, this provides a ground on both sides. So I think in that case, they put a Y delta with a Y, and then they just did a zigzag on the low side.
Andrew, yeah, I had to take a quick work call, but I wanted to mention in as far as transformers and generators go, the delta configuration you'll see a lot in the maritime world, and that's because when ships are out to sea, they don't want a fault right on a line. So there's another IEEE, it's IEEE 45 as a standard for power installations on for shipboard, and there's a lot of information on there about that too. So I just want to mention that in case anybody ever want to take a look at that. So it's pretty short standard, but a lot of good information.
Well, the hull can be a ground, right? So
and actually my project, I used the hull as a ground, and I had to for because I had a bunch of VFDs and stuff like that. But you know, one of the things is AC current does not cause steel to oxidize, but DC current will with the salt water. So there's a very there's all these special things with shipboard installations that you have to keep in mind. But they also typically isolate circuits for a single phase circuit. Usually they use double pole circuit breakers to break the neutral. So when you open a circuit, it's completely isolated. But yeah.
So when you say that you used a ground on a delta configuration, you grounded one of the phases, or
actually on the for my installation actually had to be a Y. So and this was and this was because we had a bunch of VFDs. So you know, you had shielding and all that stuff. So so it had to be grounded.
So Blaine, just a side topic, but I thought that was a code violation to isolate the neutral. I didn't think you the NEC allowed you to open the neutral.
You don't open the neutral. Essentially, you can choose to have you could have a grounded system, and then your ungrounded system is a delta. So we still made the single connection from the hull to the neutral in the switchgear. So that would be where your first disconnect is. And then, so essentially we still followed the National Electric Code. Fun fact, for any ships in the state of Maine that are under 200 feet, you can practice engineering without being a licensed engineer. And you can also perform electrical work without being an electrician. So just keeping that in the back of your mind.
Thanks, Blaine. So I've included the sequence networks for each type of transformer. The positive sequence network will look very similar for each type, right? That's always the same. It's the zero sequence that matters when you're applying different types of transformers. So again, the YY that's grounded on both sides is a path for the zero sequence fault current to flow through. A YY transformer, even if it's grounded on one side, is an open circuit in the zero sequence network. And obviously YY ungrounded on both sides would also be an open circuit in the zero sequence network. And then, like we talked about, a Y delta would be a source on the high voltage side and would be an open circuit on the low voltage side. Delta Y, the exact opposite. And then delta deltas open in the zero sequence network. If you had a grounding resistor in your Y neutral connection, that would go here, and it would be 3 times whatever your impedance is for your neutral grounding resistor or reactor or combination of the two. That would go right here. Okay. Transformer failures. Transformer failures are relatively infrequent, I would say. Definitely distribution and line faults are far more common. But when transformers fail, obviously it's more impactful to your system because they're more expensive pieces of equipment. They're harder to repair. A lot of times there's only one, and if it faults, you know, you're kind of out of luck unless you can tie load over through another circuit or transmission line elsewhere. So they're not good when they happen. So we want to have good protection for our transformers. Things that can cause stress on the transformer during its useful life are expansion and contraction due to changes in temperature, the vibration of the transformer, through fault current. If you're seeing faults on the low side of the transformer repeatedly, every time you have one of those, you've got mechanical stresses due to the electromagnetic field on the windings and the core to supply that fault current. And you can also get, if you have a transformer that doesn't have forced cooling of some sort, or if it's continually overloaded, you can get excessive heating, which can damage the transformer over time. So these stressors can cause the transformer winding insulation to fail over time. The failure of the transformer winding insulation can lead to faults and thus the need for transformer protective relay. So this I took from the IEEE guide on transformer protection. Oh yeah, I got it right here. So it just kind of breaks down the different types of faults transformers are likely to see based on the percentage of total. Looks like winding failures are the most common. You might have tap changer failures. This would be your load tap changer or your no load tap changer that can fail. Bushing failures is the next most common. Terminal board failures is pretty infrequent. Coil failures themselves, and then miscellaneous other failures. So transformer differential protection is very much similar in concept to bus differential protection, which Brandon went over not last class, but the class before. It's often used on transformers. Basically, if you have a transformer that's greater than 10 MVA or so, it's going to have transformer differential protection. From 5 to 10 MVA, in my experience, it's kind of hit or miss. It may be that the transformer has breakers and transformer differential, or it may be fused. It kind of depends on the application. And then generally below 5 MVA, you're looking at a fused transformer. Transformer differential protection is very fast protection. And when it's designed and set correctly, it's very secure, very reliable. It's really good protection. And the transformer should trip a lockout relay that trips the breakers on the high side and the low side, if it's got a low side breaker, and block the breakers from closing again so that somebody can go out and inspect the transformer before it's re-energized. Did they talk about lockout relays and stuff in the other classes? I might have
Yes.
missed that.
We
Yeah.
did.
Okay. All right. Good.
86 devices. We covered that
Yep.
fair amount. Yep.
Okay. Good. So that shouldn't be new to you then. Like I said, Brandon did a great job describing bus differential protection. So I'm gonna kind of just piggyback on what he described, and rather than rederive it from the beginning, since you just saw that. But we also, when we're doing transformer differential protection, we need to also consider the turns ratio of the transformer, and also the transformer characteristics, such as the winding configuration, whether it's delta Y, 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 delta, delta, those impact the transformer differential protection. We also need to think about harmonics, which isn't an issue with bus differential protection, and we need to consider inrush when we're looking at transformer protection. Inrush is the initial current that that's fed to the transformer when it's initially energized. It can be impacted by like the hysteresis in the core. So you can imagine, you know, the core is a big magnet, right? And you're injecting currents into the windings, and that's creating the magnetic field in the transformer core. When you open up the breakers and you isolate the transformer, whatever flux was in the core, like it stays there, like that. It's magnetized in that orientation when you opened it up. So when you go to re-energize it, it could be that the flux in the core was pointing straight up, but on the waveform, when you re-energize it, the flux needs to be going in the exact opposite direction. And that can cause a big inrush of current to try and change the direction of the magnetic flux in the core. And that's part of the reason you get inrush. There's also, it's magnetizing load of the transformer. It's nonlinear. It decays, relatively quickly, on the order of, well, it depends, but the IEEE guide recommends looking at 1 second and 10 seconds for inrush. Usually you're only worried about like the instantaneous inrush. So this is kind of a simplified depiction of transformer differential protection. And you'll notice that you can't really tell that this is different than a bus when you're just saying that this is the protected equipment. And that's because we're going to compensate for the transformer's properties in our CTs and in our transformer differential relay. So this is the traditional, quote unquote, way of doing electromechanical transformer differential protection. In a traditional differential protection scheme, what you try to do is on the delta connected winding, so this is a delta Y transformer. On the delta connected winding, you connect your CTs in a Y, and then on the Y connected winding, you would connect your CTs in a delta. And what this does is two things. One, you can set up your CTs to remove the 30-degree phase shift for the transformer such that you can compare the currents directly. And two, it removes the zero sequence current from the grounded neutral of the Y connection. So if both of these were set up in a Y CT ratio, ignoring the 30-degree phase shift, and you had a ground fault on this side of the transformer outside of the zone of protection, you would have ground fault current flow out of the neutral and towards that ground fault. Well, as Paul so succinctly put it, if it's flowing in the primary, it's got to be flowing in the secondary. Well, that zero sequence current is circulating in the delta winding. It's not going through these CTs, so it's unmeasured. So if you're measuring current on this CT and not measuring current on that CT, well, that's a difference, and you're going to potentially trip for an out of section fault. So those are the two reasons you would traditionally connect the Y winding CTs in a delta. Those are the two benefits. And ideally, what you do is you set your CT ratios to basically be the inverse of the turns ratio of the transformer, right? So if this is say it's 2 to 1, then if your CT ratios are 1 to 2, then the secondary current is going to be the same heading into your differential relay, which is pretty nice. Now you don't need to do anything else. You've compensated for the phase angle shift. You've gotten rid of your zero sequence source. You've undone the turns ratio of the transformer, and now it's exactly like a bus differential relay. So now that's pretty simple, right? Now it's just Kirchhoff's current law. Is there anything else I wanted to say on this? Oh, yeah. So if you can't, which in practice usually you can't, set your CT ratios to undo the turns ratio of the transformer, because you're usually limited to the number of taps you can have. Like, this isn't a continuous CT ratio, right? You can't set it from anything from 1,000 to 5 to 1 to 5, right? You've got a certain selected number of taps that are available to you. So if you don't have CT ratios available to identically match the inverse of the turns ratio, then you're going to have a mismatch in the current to the transformer differential relay, and we need to account for this. And so the transformer differential relay will have auxiliary CTs in it with different taps that you can then use to adjust for that difference in current, in secondary current. And you try to minimize, you use those taps to try and minimize that mismatch going into the transformer differential relay. So I thought this was a pretty good example. This was from a class, a Schweitzer engineering class that I took back in 2012. And so it's basically this same diagram here, but they provided the MVA rating of the transformer and then the turns ratio of the transformer, and left it to us class participants to calculate the CT ratios, the desired CT ratios, and the taps for the relay. I thought this was a really good example, so I included it. And this kind of goes through how you would do this if you had an electromechanical transformer differential relay. And we'll kind of walk through this, and there's a homework problem that's similar to this. Yeah, so this talks about having the different taps, and what you're looking for in the taps is for your current into, so I1 is the high side current, and then I2 is the low side current, and tap 1 is the tap that the high side current is going into, and tap 2 is the tap that the low side current is going into. And you ideally want that ratio to line up. So the first thing you'd want to do is determine what your current is at the nominal rating of the transformer into each winding. Okay, so 30 MVA at 115 kV is about 150 amps. Then you want to make sure that you're not overloading your thermal rating of your CT. So your CT ratio needs to be something that's higher than 150 amps. So I chose the 200 to 5 amp CT, right? That way you're not going to encounter a thermal limit on the CT. 30 MVA at 13.8 kV is about 1255 amps. So again, I chose the next highest CT ratio to avoid thermal limitations. So because you've wired your CTs in a delta, the current that's actually supplied to the relay is the square root of 3 higher. Okay, because they're wired in the subtractive method, just the same way, you know, from before, right? The line current into a delta is the square root of 3 higher than the actual winding current. Same thing for your CTs. So the relay current is the square root of 3 higher than the calculated current for the winding. Okay, so if you then take the ratio of CTR2 and divide it by, not CTR2, the current I2, and divide it by I1, then you get about a ratio of 2.05. Okay. And so then this is a cool little table here. I hadn't seen this done this way before, but it certainly made it a lot easier for me to visualize. This is each tap available divided by the other tap. Okay, so if you selected 2.9 and 2.9, you'd get a ratio of 1, right? So we want to calculate basically tap 2 divided by tap 1 to be equal to I2 divided by I1 to compensate for these differences in current, right? We want this to be equal to that, and we can do that using those aux CTs. So these are the taps available, right? And this is just a table of, tap 2 to tap 1. Okay, so I selected taps that gave me a ratio as close as possible to 2.05 to minimize the amount of mismatch of the current going into the differential relay. And the closest one was 8.7 for tap 2 and 4.2 for tap 1. Okay, and that was the result. So this is how you would do that, and you can calculate the mismatch. I don't think I had a slide on that, but you can calculate the difference that the relay is actually going to see in operate current versus what would be ideal. And again, you want to try and keep that as small as possible. So probably you'll rarely, if ever, have to do this anymore, because now this is all done digitally and we can program the relay to do these compensations for us. We don't have to wire the CTs in a delta anymore. We can wire them in a Y, and the relay can do the calculations, and we'll go over how a digital relay does this. But it's important to understand the concept of how this works, why it works, and how to do it. So any questions on this? Okay. All right, let me just get a drink of water here. So as I said, in newer installations, you're far more likely to encounter a microprocessor-based transformer differential relay rather than an electromechanical relay. This offers a lot more flexibility in the implementation of the protection. You can do cool things like harmonic restraint. Often the relay can also do backup overcurrent without needing a secondary backup relay. And we don't need to wire the delta CTs into the relay anymore. And we can set the relay to account for the transformer winding connections. And there are a lot of guides. A lot of the information that I referenced, like I had said last class, went through a ton of different derivations of how and why you set a transformer differential relay for a transformer that looks like this or like that, or with these connections, or you've got two in parallel and you want to use one transformer differential relay. What do you do? I chose not to do that for this course because I think, this is most often what you're going to see. And if you understand this concept and you have a particular application that doesn't line up with it 100%, that, or hopefully I'm demonstrating to you or explaining to you, or teaching you that if it doesn't line up with this 100%, well, you need to go and look at another guide on that specific application. You need to read the instruction book for your relay manual, whatever. So I chose not to go through all those different types of applications, and I'll leave that to you to do if the need should arise. So this is kind of an example of, you got a 3-winding transformer, and, how do you connect this up? Well, I don't think that's as helpful as going through the most common application that you're going to run into, and really diving into that. So what we're going to do is go through an example of how to set a Schweitzer 787. It's going to be similar depending on the relay make and model, but there are some things that you're always going to have to do, and then there are some things that you'll likely or often need to consider or do, and we're going to kind of run through those. So you're always going to need to set the CT ratios, obviously. You're always going to need to set the tap settings, like we just talked about for the electromechanical relay. A lot of times, actually, in digital relays, they'll automatically calculate the tap for you. You put in the MVA rating and your CT ratios, and it'll give you the tap. So you don't even need to worry about that. You'll need to tell the relay what type of transformer it is, the winding configurations, or the compensation settings, and we'll talk about that. And then just like Brandon explained for your bus differential relays, often you'll have either a single slope differential characteristic or a dual slope characteristic. And he talked about the difference there and how to set that up. So it's similar. Additionally, for transformers, you'll often need to consider whether or not you want to do restrained harmonic restraint or blocking. And if you have an unrestrained operate current. So that would be an instantaneous differential element that's kind of separate to the typical restrained element that operates on the curve. This is like, it's the fault current is, the differential current is so high that it couldn't possibly be an external fault. It's got to be an internal fault, and don't wait for the restraint calculations, just trip. So again, this is from the 787 relay manual, if you're curious, but this is one of the examples that they provided, and I think it's a pretty good one. So we've got a delta Y transformer. It's delta on the high voltage side, Y on the low voltage side, and the Y neutral is grounded. So this is, pretty typical transformer. The H1, H2, and H3 bushings are connected to A, B, C respectively, which is nice. And then the A phase current is wired into the A winding 1 input, B to the B, and C to C. So there's no trick here as far as the CTs go. They're all wired as you would expect. Winding 1 is the high voltage winding, and winding 2 is the low voltage winding. Again, I would typically see that. That's pretty common, but it could be the other way, and you just change the settings accordingly. That doesn't matter. But we need to know it for our setting up the relay. We need to know which winding is wired into which input. And then they provided this kind of example nameplate for the transformer. So this is a 7.5 to 10 MVA transformer. It's 13.8 kV to 4160. And looks like it is a DAB transformer. Yeah, it is, based on the vector diagram. So that's our transformer. Looks like it's got a no load tap changer, no LTC. Again, we talked about this. We can tell because it's got letters here. So it's got no load tap changer on the high side. Doesn't look like it's got an LTC on the low side. So these are the settings in the relay that we'll need to consider and set. These are in the settings file. I think these are in like the transformer information section, and then these are in the differential section, which is why they're two separate snips here. So first we'll set up the general transformer information. The CT connection is, anybody want to guess what that is? I hadn't thought about this. Yeah, we can do this together. Let's do it. Who wants to tell me what the winding 1 CT is? Is it Y or delta?
So that one's Y.
Yep. Okay. So we're going to set that to Y, and then the winding 2 CT is
That one's also Y.
are also Y. So we're just going to set those to Y. The CT ratios. Got to set the CT ratios. Oh, it actually doesn't give it to you. Well, that's no fun. Well, pretty self-explanatory. you put in what it is, right? So we don't have to go back and look. But then we set the transformer maximum capacity. So what would that be?
ten thousand kVA.
Yep, 10 MVA. It wants MVA, but yeah. So 10 MVA. Okay. The next one is whether or not you need to define the CT compensation. And in the manual, basically what it's saying is, do you have a transformer that you need to describe what it is? You know, do you need to set up a phase angle shift? Do you have a yeah, I guess that's what it is. It's a phase angle shift. Do we have a phase angle shift for this transformer that we need to worry about? Or the other one is there a ground source inside the zone of protection? And the answer to both is yes, right? We got a transformer that has a phase shift, and we have a ground source inside the differential protection. So we need those compensation settings. So we're going to set ICOM to Y. The compensation, we'll talk about those in the next slide, but that's the next thing we need to set. And you'll see that the options are from 0 to 12. Right, so those are the clock settings. So we'll talk about that. The winding 1 line-to-line voltage. What's the winding 1 line-to-line voltage?
$13.8.
13.8. Yep. And the low voltage?
4160.
4160. So we're going to set winding 1 line to line to 13.8 and winding 2 to 4.16. And so now we're done with that section. Oh, well, minus these settings, but we'll talk about that. So as we've talked about extensively, I hope everybody's pretty comfortable with this now. We need to determine what the phase angle shift is for this transformer. Okay, so we need the transformer vector diagram, which is provided here, and we need the AC schematic that shows the phase to transformer bushing connections. We need the CT connections and the CT to relay connections. So the nameplate for our transformer, like I said, is here, and we have an H1 to H2 to H3 sequence of ABC. So what is our vector diagram? Is it a DY1, DY11, YD1, YD11? What is it?
Y1.
DY1. Yep, that's what it is. All right, so this kind of goes through that. We're assuming that our system's phase rotation is ABC. If it's ACB, it screws it all up, right? It's reversed, but typically it's ABC. There are some utilities. I've never worked with a utility that has an ACB rotation, but I understand that there are some out there. I don't know why they do that. That would just confuse me, but all the ones I've worked with are ABC. Pretty good assumption. So we also, the standard phase CT connections, excuse me, are used, right? We have A to A, B to B, C to C, so we don't need to do anything with our settings to compensate for that. You can wire these CTs any way you want, you know, and you can compensate that for that in the relay settings as long as you understand that and account for it. But in general, it's good practice to wire the A current into the A input and vice, then, and so on.
Hey, Andrew, can I ask a quick
Yes, go ahead.
question?
Yeah.
Because you talked about the CT compensation for position 1, but if do you want to talk about if it's a YY with the 12 o'clock and the 0 position?
Yes, I
Okay,
do.
you can
Yep.
do that here in a bit.
Yep.
Okay, sorry about that. Thank you.
No, no problem. No, good point. Thank you. Yeah, CTs are configured in the Y. Everything's wired up in good practice, as you guys have gone over in your AC schematic classes and relay 1 line classes. This is all looking good. So this is going to be an easy relay to set. So yeah, this is great. All the connections are standard in accordance with good engineering practice. This makes it much easier to set our relay. Many applications do not conform to this standard. In my experience, it's, very often it is. There's actually an interesting instance that I'm aware of. I've reviewed the settings for it, but not just because I was looking at them for other purposes, not because I was involved in the project. But CMP system, interestingly, their entire system 115 kV and below is numbered 1, 2, 3. That's how they have their phasing. But at 345, I don't know if you're aware of this, Paul, you'll be interested to hear this. At 345, they don't use 1, 2, 3. They use ABC. And A is not phase 1. A is phase B. And C is phase 2. And A is phase 3. So the rotation is the same, but they just chose different labels. And I don't know why that is. The only thing I can speculate is, CMP is kind of an older utility. They've been around a long time. They probably standardized on 1, 2, 3. And then, they had their system set up that way. And then they brought in 345 and probably to match the utility that they were interconnecting to, whether it be Bangor Hydro at the time or Public Service of New Hampshire or whomever. Maybe they had phasing of ABC and they wanted to match, and then they went to go tie it in. They were like, oh yeah, it's not, A isn't 1, so they had to just say, okay, well, B is 1. Well, when they wired in the CTs for the relay, this is ABC, say, and this would be not 1, 2, 3, it would be 2, 3, 1. Right, because A would be in phase with 2. Do I have that right? B is 1. B is 1. So this is 1. So this would be 1, 2, 3. So A would be phase 3. Okay. So they wired in the CTs for ABC into ABC, and then they wired in 1, 2, 3 to 1, 2, 3. So now we actually needed to account for that difference, even though everything kind of looked right, but because the phases weren't the same, that needed to be shifted. So there are instances where you may need to take account for the CT connections from the CT into your relay. It's pretty rare, but that's an interesting, I think it's an interesting anecdote. So okay. Because we've wired this in as you'd expect, makes it much easier to set the relay. So this is another reason why you want to pay attention to that when you're doing your AC design. It helps us protection engineers and you in the future to set your relay. But you need to keep an eye on it in case it's not standard. So this is the guidelines to setting that winding configuration setting. What we're trying to do here is we're building towards the setting of these winding 1 CT compensation and the winding 2 CT compensation. So we need to determine the phase shift in primary load current. We already said that's DY1, so the low side lags by 30 degrees. And we need to determine if there are non-standard CT connections, which there aren't, which helps. Then we need to select the reference winding, okay? And the guidance is that if a delta winding exists and is wired into the relay, choose the delta winding as the reference. And you select the winding that's a delta as 0, which makes it your reference point. Then if a grounding transformer exists on the delta side of the transformer within the zone of protection, you need to set it at 12. And the reason you need to do that is, say there was a ground bank here, right? And you set this compensation to 0. 0 does not remove the 0 sequence current from the differential operation of the relay. Whereas 12, you can see, 0's here, right? So is 12, right? They're the same. So you'd say, why do you set it to 12 instead of 0? 12 removes that 0 sequence component. So if you had a ground fault over here, the grounding transformer would provide 0 sequence current. You're seeing that in this CT. You're obviously not seeing it here because it's not flowing out of the transformer. It's flowing from the ground source. And so your differential relay would trip, potentially trip, for an out of section fault, which we don't want. So that's why, that's the difference between 0 and 12. Where am I? Okay, so we're going to set this to 0 since we don't have a ground source inside of our zone of protection on the delta side of the transformer. If a delta winding does not exist, select one of the Y windings as a reference and choose 11 for the compensation. And this is what Paul was talking about. You don't want to use 0 because there's a divide by 0 error that you can get. And it tells you to use avoid even matrices whenever possible. So there's some sort of scenario where you're applying the compensation matrix to the currents that it's measuring, and you can get a divide by 0 error, and the relay doesn't like that, obviously. So to avoid that, if you had like a YY connected transformer, at least I would intuitively go, okay, well, if the neutral windings aren't grounded, I could just use 0 0, or if they are grounded, I could use 12 12. They say don't do that. Use odd matrices. So you'd set it to 11 and 11. So keep that in mind. So then you determine the required compensation setting for all other windings. So we've selected our delta winding is 0. Now we need to figure out what our Y winding needs to be. If you have another delta winding, set it to 0. That's assuming that it's, no phase shift in the delta winding, which is, if you have a delta transformer, it probably doesn't have one. And then again, use odd matrices for compensating Y windings whenever possible. So in our case, we've got our standard phase to bushing connections. So in order to determine what our compensation needs to be, the phase shift in the primary load current is such that the low side winding lags the high voltage winding by 30 degrees, like we talked about on the vector diagram. And there are no non-standard CTs. So the way I really dislike the way that this is described in the manual, and I understand why they do it, but it's confusing to me. And the way I think about it, I think is easier to understand. So the way I think about it, I'll explain that first, and then I'll go through what they're talking about here. This is exactly our situation, right? We have the delta at 0, and we have the low side at 30 degrees lagging. That's exactly what this is showing. So to me, if this is at 0 and my low side current or low side voltage is at 1 o'clock, I would just set it to 0 and 1, and you're done. Away you walk. That's not how they describe it. Although that works. That's what our settings are going to be. The way that they describe it is for load current, right? If you were to have current going through both sets of CTs, then because it would be coming out the current would be going into the non-polarity side of the CT, and that's what's going to the relay. The actual current seen by the relay lags or leads by 150 degrees, right? Instead of lagging by 30. That's what the relay is actually measuring. Okay. And so they say, well, the current for IAW2 is leading by 150 degrees, and you would need to shift it 30 degrees forward in order to be 180 degrees out of phase with IAW1. So then you'd set it to 1. So the result is the same. I think their ways of doing it is a lot more complicated. But the reason you need to know to do it that way is if you have non-standard CT connections. You can't just look at the clock position anymore. So that's why it has to be kind of like in a broad form described in this method. Whereas I like, as long as everything's connected the way you expect, it's 0. And then the other winding is the clock position, 1 or 11 typically. Okay. So for our settings, we already kind of went through this, but there's a delta winding, that's CT winding 1. So we'll use that as our reference winding at 0. The other one says like if there is no delta winding, so that doesn't apply to us. And then determine the required compensation setting for IAW2 must be rotated 30 degrees, 1 multiple of 30 degrees in the counterclockwise direction to be 180 degrees out of phase. That's what I just talked about. So you'd set it to 1. So resulting settings for the CT compensation settings is 0 and 1. And then this is just talking about what I just did. That's confusing to me. This is the way I think about it, as long as everything's connected the way it should. Okay. How are we doing on time? We only have 5 minutes left. Why don't we, I guess we'll stop there and we'll get into the differential settings next time. We've set up our transformer, kind of all the fundamental properties. We know the MVA rating, the CT ratios, we've compensated for the phase angle shift of the transformer. We've determined whether or not the CTs are a Y or a delta. So I think that's probably a good place to stop. And I'll open it up to you guys for questions or comments.
I have a question. When you said use odd matrices, I just wanted to make sure I understood. Does that mean the value you're setting in the compensation should be an odd value?
Yes.
Okay, thanks.
Yep.
Any other questions for Andrew? Okay, thanks very much, everyone. Have a great day and see you all next Tuesday. Take care.
Thanks, everyone.
Take care.
Thank you.
Thank you.